So I'm Ryan Myers. I'm also one of the researchers out of the London NRC office. My background is in mechatronics engineering, a lot of focus on creating CNCs and robotic systems into manufacturing. I did a fair bit of work with mobile robotics as well. And that sort of led me into this domain to sort of help out on this project. So what we're going to be talking about today is robust detection for young vulnerable road users in diverse lighting and weather scenarios. So this is obviously a big challenge. We have Canadian weather where we have snow, we have lots of rain, sleet, hail, you name it, which makes it kind of challenging for a lot of these type of systems to actually have good detection of especially vulnerable road users, so smaller children, people who have taken up less pixel space than let's say the average adult. So we have a lab at our office in the NRC in London, focused specifically on CAV, so connected and autonomous vehicles. Inside of that lab, we have a nice group of sensors that we're able to sort of work with, a large library of LiDAR systems, electro-optical vision cameras, infrared cameras as well, that we've integrated into our vehicles, and we use these as a way for us to work on projects scaling from mapping, modeling of sensor performance under various conditions, developing these type of detection and classification algorithms for, like I said, vulnerable road users. And we've tested them on a variety of platforms, either through our own data collection locally, or as well as against generalized data sets that we have. So you can see some images of our lab and some of the equipment that we have set up inside of these vehicles. So the actual problem statement and the motivations. So as I said, children are at high risk. They don't sort of follow all of the behavioral patterns that we learn as adults, right? You're playing with balls, things like that. There's a good opportunity that you'll see somebody having some abnormal behavior running into roads and sort of providing a challenge for drivers. So it's very important to sort of have good detection and observation as to these people, especially in as much advanced notice as you possibly can. The other thing is when you have visibility issues, so like I said, weather conditions or potentially things like hedges, which are causing obstructions or occlusions to these type of individuals, it's important to be able to have models that are generalized enough to be able to make those type of inferences, right? So if you can only see the upper shoulders and the head of a kid because he's hidden behind a hedge, you still want to know that there's an object of importance there rather than ignoring it and potentially dealing with the consequences later on. A lot of the existing models that people are using for these sort of classification applications, right? So YOLO is a very popular algorithm. They're not trained for detecting young pedestrians. So like I said, as you end up taking a smaller amount of pixels, detection becomes more and more challenging, right? So we've decided to take a look at that through the data that we've collected in previous projects as well. So what we've done is we've actually taken, built our own sort of detection model based off the YOLO framework, and we've named it the LTV YOLO. And this model is specifically focused on detection of young road users, particularly using thermal vision that we've, like I said, augmented onto our vehicles. So the model itself, we found it has significantly better performance relative to the more standard classification models, and one of the reasons is that we've been able to find that with using thermal cameras, we can scale down the input to be significantly smaller, so we can get good frame rates through using this model. In addition to that, we also have much less parameters that we're using to do that type of classification, rather than the larger models of things like YOLO 11 and 12. This allows us to sort of have it running in the vehicle on edge devices, things like Jetsons. We were able to deploy it and get very good frame rates, which makes it very useful for real-time applications. And obviously very similar to YOLO, it's all predictions are made in a single forward scan. So in terms of how we went and collected this data, so like I said, some multiple projects that we have going on have us looking at a wide variety of driving conditions. So we do data collection in snow, we do data collection in rain, and we've been able to sort of consolidate all of the data that we've parsed through it and been able to sort of annotate the young vulnerable road users through it at those instances. So we've got thermal cameras, LiDAR data, and we've got our standard RGB cameras that have timestamp data related to it, so we can sort of intermingle the data sources for ease of use for annotation and for training of our models. So obviously some of the challenges associated with it is when you have large data sets, you actually have to go and manually do that type of annotation, which is very time consuming, but I mean the results are the outcomes are very important. So the other things that you can encounter, especially when dealing with thermal cameras, is it can be challenging to sort of discern the different objects, right? So depending on their positions, the clothing that they're wearing, in terms of the RGB space, can make it very challenging to do that annotation. A good example is if you think about children with parents, right? A lot of the time they're walking close together. How do you actually discern which one's which? Especially if they cause occlusion by sort of hiding behind them or walking behind them, right? So it can be challenging to do that component of it. There's also no public data sets that are specifically tuned to train or to be used for training on children, probably for good reason, but the data sets that we have, like I said, are generalized and more focused on adults, right? So that's generally what these training sets are built around. So. And now we'll have Abdullah come in and talk.
So what we are trying to achieve. So here we are developing our lightweight model that basically overcomes all the heavy duty and heavy lifting from power computing that we require, just like how we use it in our regular object detection models. So we try to scale down these models to let it able to be work and run on edge devices. So that is one of our main objectives, to be able to deploy these models whatever we want. So we improve the detection accuracy with the young vulnerable road users, aka kids, and in different adverse weather, lightning, day, night, in a very high risk crossing pedestrian area, for unexpected kids area. So, and also we are enabled to run a real-time detection on smart surveillance cameras, and also on automated and autonomous systems. So here's a comparison between, in a chart form, numbers between our developed model that built on top of the architecture of YOLO, compared to the latest YOLO 12 and YOLO 11, where our model was capable to show a higher accuracy with a 78.5 in thermal and low light, where that was our main focus on, especially during winter season and snow, as well as we successfully achieved to hit approximately 50 plus frames per second. And also with the model size, we were able to reduce the model size in terms of megabit, and to be able to optimize those models on edge devices, as I mentioned earlier. And also these models have, this model had able to handle fog and snow, and as compared to YOLO 12 and YOLO 11. And in terms of depth-wise and in terms of convolutional neural network, we managed to reduce that size as well by reducing the number of layers. So here is a comparison between the robustness between our developed model compared to YOLO 12 and 11, where you can see with that simple scenario where there's a kid walking next side by side to his dad during while our research vehicle is moving around doing data collection for one of our other projects, where we had high detection confidence during snow, as well as in a low light compared to RGB cameras. In rain seasons, we still remain to be seen, because we still this project research still is ongoing. So the data collection for rain, unfortunately, I guess we missed it out. So we will wait when rain doesn't come. And we can see the comparison in percentage between YOLO 12 and 11 compared to our model, that we managed to have a very high performance among all. So here are some sample images while we were crossing at one area where kids are gathered, and our model showed very good performance. We still like having a very small data set, so we still like growing that data set. And definitely when with deep learning models, when models data set growth, models perform better. So also like where we can be able to use this system as well. So this system is able to be used in intersection safety monitoring, just like what you can see in that running video, where that is a very high-risk crossing area where the train is passing by and pedestrian is about to cross. So that crossing area is considered one of the objectives that we are looking at to deploy our models and our system, as well as with autonomous vehicle to improve perception using thermal cameras. And at the very high-risk area, just like around schools where there's like all the kids is running out from their school, especially after school is over and running to go to their buses, where that area is considered one of the also high-risk area for kids, especially in winter or dark light events. So takeaway notes. So that we improved our proposed model, the LTV model, in terms of detecting the vulnerable road users, and we successfully deploy our lightweight model in terms of to be suitable to be used on edge devices. And future work, we still, as I mentioned earlier, we're still working on collecting data in a very different weather condition, daylight condition, and to be improved, to be generalized to multiple applications. And moment of truth is testing the model in a real-time scenarios. So that's all for me, and I will be more than happy to have your questions.